In the last video, we took a look at the critical value approach to hypothesis testing. This one will look at the p-value approach. In the previous one, for critical value, you found that test statistic, then you found the critical value based on the significance level. You compared them to see whether the values were on the outside, in which case you have enough evidence to reject the null hypothesis, or on the inside, in which case do not reject the null hypothesis. This is the p-value approach. Both of these approaches were working under the assumption that we know the population standard deviation. Eventually, we'll get to the point where we look at what happens if we don't know the population standard deviation. So this is sort of the introduction. In the next section, we'll tackle some of the application problems, and we'll compare the two approaches. So the p-value is the probability, essentially, of a type 1 error. So it's a probability that you reject the null hypothesis when you shouldn't. That means that that p-value should be very small. If your p-value is too big, then you're saying there's a high probability that you're wrong. So the p-value is calculated from the test statistic. So we're going to look at the area to the left or to the right, depending on whether it's left-tailed, right-tailed, or even two-tailed. And then we're going to compare that to our significance level to decide whether to reject the null hypothesis or retain the null hypothesis and not go in favor of the alternative hypothesis. So the p-value is essentially the probability of getting sample data that's at least as inconsistent with the null hypothesis as the data that we actually have. So if your p-value is very small, then that's a much stronger case than a very large p-value. So let's go back to my example I had done with test grades in a previous video, except this time we'll do it with the p-value approach. So I claim that students on my test score very well, about 86% on average. You look around you at the class and you don't see a whole lot of 86s or above. You think that I'm overestimating things. You think that the average grade is actually less than an 86. So you take a sample of 25 tests and you make a list of the grades. So your null hypothesis is that the average is 86 because that's what I'm telling you, right? The null is based on some fact or some information that you already have. In this case, that the mean is 86. The alternative hypothesis, you claim that the average is actually less than 86. So less than 86 makes this a left-tailed test. Okay, we're going to look at values to the left of 86. So from that sample, I calculate the average test score as 83.5%. So I can start making a list of things that I know. The sample mean is 83.5. The null hypothesis mean is 86. Somehow you found out from me that the standard deviation for my tests are 6 points. I want to know if I should reject the null at the 5% significance level. All right. So the first thing I need is that z statistic, that test statistic. So just like for the critical value approach, I have to calculate z. So if you remember, z is the sample mean minus the mean from the null hypothesis over the standard deviation divided by the square root of n. So in this case, n is 25 because I told you that I took a sample of 25 tests. All right, throw the numbers in, and I get 83.5 minus 86 over 6 divided by the square root of 25. Let's grab a calculator and see what that gives me. 83.5 minus 86. The numbers on the bottom are nice, right? The square root of 25 is 5. 6 divided by 5, 1.2. So I get a z-score of negative 2.08. Not surprising because my test is left-tailed, so I'm assuming I'm to the left of the mean anyway. All right, so now I got to go to my table. All right, let's pull up that table of z-scores here. This is the formula card if I go down far enough. Rotate it to the right. All right, so now let's look at negative 2.08. All right, here's negative 2.0. 1, 2, 3, 4, 5, 6, 7, 8. There it is. 0.0188. Which, if I want to write it in 2 decimal places, I could write it as 0.02. Okay, that's my p-value. That's my significance level. 0.02 is less than 0.05, which means that my p-value is less than alpha. So from this problem, I claim a 2% probability that I'm going to make an error. I'm willing to accept up to a 5% possibility that I make an error, so I'm okay. So at this point, I can reject the null in favor of the alternative, meaning that there's enough evidence to suggest that the average score on one of my tests is not 86%, that it's actually less than 86%. It's not going to give me a number, right? It's not going to guarantee me that my test scores are exactly 83.5%. What this is saying is based on the test scores, the sample mean, and the standard deviation, there is enough evidence to say that the mean is actually less than what I'm claiming. Now, you notice that the significance level plays an important part here, because suppose that instead of having a 5% significance, I said I wanted it at the 1% significance level. Well, now, do not reject, because now I'm only willing to accept a 1% error when I calculated it was a 2% error. So at the 5% significance level, it's okay. I can reject the null in favor of the alternative hypothesis. But if I want it at the 1% level, then don't reject. All right, so as funny as it sounds, the lower the p-value, the stronger your case against the null hypothesis. So if your p, and we're talking like 10% or less, we're not talking like 50-50 chances here. So if your p-value is above 10%, then you have really very little, if any, evidence against the null hypothesis. If your p-value is between 0.05 and 0.1, all right, then it's kind of moderate. Strongest is less than 0.05. Very strong is less than 0.01. One of the reasons that this p-value approach is helpful is because if you're reading somebody's study or a research article or something, and they tell you that I did this and the p-value was 0.005, then you know you've got a very strong case against that null hypothesis. Right? On the other hand, if you're reading it and you see the p-value is 0.2, then you go, why did you even publish it? This is not a worthy study because that p-value is so high. All right? So that p-value gives us a little bit more information than the critical value approach. All right, so let's take a look at this problem here. I don't want to put the answer up, so I'm going to stick this at the bottom of my screen. Determine the p-value, decide if the null hypothesis should be rejected at the 5% level using a right-tailed test with z equals 2.03. All right, so I've already been given the z-score of 2.03. It's a right-tailed test. Now, what do you know about that normal curve? You really want, if it's a right-tailed test, the area to the right of 2.03. You're looking at this area here. But when you look at that table of z-scores, it's going to give you the area to the left. Well, you can do that, right? You can find this area in here and then do 1 minus that area, and it'll give you the area on the right side. Or what if you just found the area at negative 2.03? Okay, by symmetry, this area here is going to be the same as that area there. So let's look at our z-score table for z equals negative 2.03 and see what that gives us. All right, 0, 1, 2, 3. I get 0.0212. And that is my p-value, right? That p-value is the area either to the left or right of that z-score. So at the in this case, it said 5% significance level. So at the 5% significance level, again, almost exactly the same numbers as last time, that p-value is less than alpha. So I'm willing to accept the 5% error. I've calculated only about a 2% error. So yeah, I'm good. 2% is less than 5%. Enough evidence to reject the null. All right, here comes the interesting case. And that is, what do I do with a two-tailed test? Okay, so let's determine the p-value, decide if the null hypothesis should be rejected, 5% significance level, two-tailed test, z-score of 3.08. So now what I got to do for a two-tailed test is I got to add up both areas. All right, so I'm going to look here for 3.08, and then I'm going to look down here for negative 3.08. I'm going to take this area over here and this area over here and add them together. Well, once I found one, I found the other. So negative 3.08 is very small, 0.0010. So that's how much it is on the left, and that's also how much it is on the right. So my p is 0.0020. All right, now just watch your decimals here. The significance level we were given down here was 0.05. The p-value we were given is 0.0020. So clearly, p is less than alpha. Right? P is almost 0 in this case. So because p is less than alpha, then that gives us enough evidence to reject the null in favor of the alternative hypothesis. So if it's a two-tailed test, then you have that extra step of taking not only the area to the left, but the area to the right. All right. Let's try one or two of these, and then really that's the end of 9.3. We'll do another one for 9.4 because that gets into comparing the two different models. All right, so again, let's try another two-tailed test. Two-tailed tests can be a little tricky sometimes. So a two-tailed test, z equals negative 2.42, 5% significance level. Should I or should I not reject the null? So let's look to the left of negative 2.42. So negative 2.4012. So 0.0078 is what I get. But because it's a two-tailed test, we got to double it. So that p is going to be 0.0146. Right? To 2 decimal places, 0.01. To 3 decimal places, 0.015. So my p is less than alpha. I can reject the null. All right, how about this one over here? I can already see where this is going just by looking at it. It's a left-tailed test with z equals 1.25. So z equals 1.25 is to the right of the mean. So this thing has got to be way above any probability we're likely to accept. So left-tailed test with z equals 1.25 means I actually have to go onto my z table at 1.25 and read it across. It's going to be enormous. 0.8944. All right, because that's everything to the left of 1.25. All that area there. And so, yeah, clearly 0.89 is greater than 0.05. Do not reject the null. All right, try one more. How about a right-tailed test with z equals 1.24? So it's right-tailed, and that z is already above the mean. The question is just far enough or not. Okay. So if I want a right-tailed test with z equals 1.24, I'm going to take my little shortcut, and I'm going to go down here to negative 1.24. And I'm going to look for the area down here, which is the same as the area over there. All right, so negative 1.201234, 0.1075. The significance level was 0.05, so clearly p is greater than alpha. Do not reject. Do not reject the null. There's not enough favor. There's not enough favor. There's not enough evidence to favor the alternative hypothesis. So you're willing to accept a 5% error. You're given almost an 11% error. Too big. Not enough evidence to get away from that null. So that null is pretty strong, right? We're not going to reject the null unless we have a good amount of evidence to reject that null hypothesis. It's not like a 50-50 chance type thing. If we're going to throw away something that was already given to us, then there has to be a lot of evidence against it before we decide to get rid of it. Okay, in this case, there's not enough evidence, so do not reject the null. All right, we'll come back and do another one where we compare the two methods.